talking about the pioneering works that was based on the subgraph optimization, as I mentioned. Now, in this part, I'm going to talk about the learning-based, heuristics. As Hossein explained, in this, alluvial diagram, we can see that after 2019, we can see a paradigm shift toward the learning-based methods. And now we can say that the goal is, recommending the team by a new method based on the machine learning, techniques. But if we look at all of the works, if we carefully look at all existing works in the literature, we can see that the methods that are used in these works, all of them was the classic, machine learning techniques by, for example, the classification or link prediction. And they are not, specifically designed for the team recommendation, domain. And now, we can see that there is a room to continue the research in a way that using the different objectives and different methods that are important for the for recommending the team and changing them to the learning, learning method. For example, I mentioned different objectives which are studied in the graph optimization works, optimizing the communication cost, optimizing the proficiency, and other objectives. But the learning-based methods are not going to learn based on optimizing that objectives. Okay, they only rely on the past successful and unsuccessful, sets. And it would be a new line of research how it is possible to optimize that important and crucial objectives, but by a learning process and a learning method. How we can, modify the loss function in a way that specifically, we should specifically design the loss function that works only for team recommendation domain. And this is the idea that could start a new line of research in this domain. Yes?
What are the main target domains in this study? Companies, projects, or something?
I'm going to explain this in the following slides. Yeah, I'm going to explain this. Okay, as I mentioned, the learning-based works start in 2019 by a paper published in 2019 by Safianza, Deep Neural Network for Optimal Team Composition. And this work specifically focused on the team of the gamers, and the goal is, recommending the best team of gamers that can play together in a way that they would be successful in winning the game. The main focus of this paper was in the game, domain. And the method which is used in this paper is the autoencoder architecture. And we can see that in this paper, the training set is the set of all the history of successful and unsuccessful games. And by using, this training set, they try to recommend the team in a way that, the form team or the recommended team, gain the success and members can play in a successful way. So predicting the successful team of the gamers is the goal of this paper. It was the first, paper in this topic. And if you look at the the Google Scholar page of the authors of this paper, as you can see, Sapienza, Ferrara, and Goyal, these are the co-authors for this paper. And if we, looking, more in detail, we can see that there is one of the researchers, Gallistone, is the co-author with Ferrara and also with the Goyal, but he has not been a co-author with the Sapienza. And by providing the information about all past successful teams, we expect the model can learn from this ties and this relation, and we expect the model recommend the Galisteo and the Sapienza as the potential team members for the future works. If we generally want to mention the advantages of the learning-based methods, we can focus on the efficacy, and we can easily see the result of the papers, and we can see that the learning-based works have improved the effectiveness of the recommended team, and also they are more efficient. In less time they can get the better results, and also all the learning-based methods, we can say that they can easily handle the larger networks, and also it is possible to use them for the temporal occasions when a new node or a new expert and new edges are going to be added to the network. Okay, after this, explaining the introduction part, I'm going to continue with the definition of team and team recommendation, in more detail. At first, the definition of the team. I want to start it with an example in academia and the computer science domain. By a quick search in DBLP, we can find the list of all the authors in computer science domain as a set of all of the experts. And also we can easily find the research topics in this domain as the skills that are associated with each expert, that can be associated with the expert. By a team, we mean a subset of experts, in a way that they can collectively cover a set of skills. For example, the keyword of a paper or a keyword of a research can be considered as the skills required for that team. And this team of experts that collectively cover the required skills, is shown that are successful when they have published a paper. And in this case, a team can be defined, and also we can easily find the list of all of the published papers, and this can be used as a training set, for our models. And what does it mean by team recommendation? By team recommendation, when we have a set of required skills, the goal is learning a function f in a way that the function f can map the required set of skills to a subset of experts in a way that the output would be a successful team. And this function f, is f is a function of the parameter theta, and so the goal of team recommendation is learning such function f of theta by learning from a training set of all past successful and unsuccessful teams. Now I continue, I'm going to explain about the different model architectures that are used by different works in this domain. We can mention all the methods that are used. The first method, which the easiest one, is the feed-forward model, and as you can easily see in this method, in the feed-forward model, the input is a vector, is a one-hot vector of the skills. It means that when we have a required set of skills, Vs, the one-hot vector, each entry associated with the required skill is equal to 1, and another entries are equal to 0. So the input of the feed-forward model is the one-hot vector Vs, and the output would be the vector V sub F star, which is associated to the recommended set of experts. The main drawback of feed-forward models is that these FNN models can, overfit easily, especially when the data is noisy and also when we have a limited amount of data. And in general, we can say that the data in team recommendation domain suffer from popularity bias, because there are a majority of works, includes some, famous experts, and also, the unknown and unfamous experts, have contributed only in a few teams. So if we train if we train FNN on the data of team recommendation domain, the model can easily overfit to recommend the popular experts again and again. And that's why we can say that by using FNN, maybe we have a systematic discrimination against inadvantageous or unpopular experts. And the idea which are used by the different researchers in time to overcome this issue was using the probabilistic weights, and they tend to use the variational Bayesian neural network instead of the feed-forward neural network. And in this case, instead of simply predicting the real numbers as the parameter, the model is going to learn the distribution of the parameter instead of only the real numbers. If I want to explain it a bit more, we can say that in general, any neural network can be seen as a probabilistic model, and for example, in the classification, the output are classes, so the distribution of the classes are going to be learned, or in the regression, the Gaussian distribution is going to be learned, and generally we can say that the goal is maximizing the likelihood function f of theta, and this maximization is done by minimizing a type of loss function, for example, the cross-entropy in classification or sum of square error in regression. It was, the method which is used in FNN. But by using the Bayes theorem, we know that after multiplying the likelihood function with the prior, the distribution of prior, probabilities, we will gain the better results. But in general, the probability of weights P of theta cannot be efficiently computed. So instead of using the P of theta, the method was learning another distribution which is the nearest one to P of theta by minimizing the Kullback-Leibler divergence. And in this way, instead of the real amount of real numbers, the distribution of the parameters is going to be less. After FNN and variational Bayesian neural network, the other architecture that is used in team recommendation works is based on graph representation learning. As I told you, in FNN and also BNN, the input was the one-hot vector. But in the model, in the graph representation learning model, the idea is that instead of using the one-hot vector as an input, the researchers try to use a dense vector as the input of the model. And by a dense vector, it means that the dimension of the dense vector is less than the one-hot vector, And also, the other important thing is that these dense vectors are informative. And so, by using the dense vectors as an input of the neural recommender, it is expected to have the result. The result would be more effective and more accurate. Here, I want to mention that all the methods, all the team recommendation methods that are used in the literature that use the graph representation learning, all of them have used the transfer learning based methods in a way that at first, the dense vectors associated with the skills is learned by a representation learning method separately, and after generating the embedding vectors by RL, then these dense vectors fed to the recommender model, FNN or BNN, and then the output that are the set of experts are predicted. So generating the embeddings of skills in all the works has been done separately and before feeding it to the neural model. And now we can say that to generate the embedding vectors that I mentioned, different methods can be used, and these are the methods that are used by team recommendation works. The first method was using the MetaPass based, and the other method is based on the message passing. In the MetaPass based method, after looking at the expert network, some MetaPasses are fixed, and then the model is going to learn the dimension for the skill nodes in a way that all the nodes that are located in one of the MetaPasses have the embedding vectors near together. For example, suppose that in the first MetaPass, it is APA, A is the author, P is the paper. So author is related to paper, paper is related to the author. So this MetaPass shows that these two authors, these two are co-author in the paper P. So when the model try to make the embeddings in a way that the embedding of A, P, and A are near together, it means that the paper and the authors and its authors, the embedding of these nodes would be near together in the embedding space. So the MetaPasses should be defined and should be selected meaningful at first, and then we can say that the model from the MetaPasses can understand, can get more information, and so the generated embeddings are informative, and these generated embeddings have information about the co-authors, about the skills associated with the papers, and something like that. And after generating these embedding vectors in the first step, then it is possible to feed these embedding vectors to the recommender, and so the output of the output, which is the recommended team, would be more effective when we compare it with the version that we only fed the model with one hot vector. It was the first method.
I just wanted to add something. So how many of you have worked with neural nets? So you already trained in neural nets, yeah? So the thing is, here, I just wanted to mention that this is very important step of the team recommendations. So if I go back to this architecture, if the first input, the input layer, is of size set of the skills, and assuming that in one data set you're going to have 1,000 or 2,000 skills, that layer is going to be 1,000 by H. So the first matrix is going to be huge matrix. And also in the last layer, if you have, for instance, a pool of 1 million candidates, The last layer is gonna be h bar 1 million. So again, that would be a huge matrix. So it is just one layer neural net. So you're gonna learn two big matrices of parameters just by the data. So you need a lot of epochs, a lot of things. So these works trying to at least reduce the complexity of the first matrix. So they say that instead of just having a multi-hot or one hot vector of size, for instance, 1,000, so what if we have just a dense vector of 100? So it reduces the first matrix hugely. So that's why they go below this step. So they try to form a graph very similar to the graph in subgraph optimization, but then they apply GNN just to learn, basically you know that if you apply GNN on any graph, it gives you the embeddings of the nodes. So they just pick the embeddings of the nodes for skills, and they just simply ignore the embeddings of the other nodes, and they use those embeddings as an input layer of the FNN or BNN. So in this way, they try to reduce the complexity of the phase matrix, and they obtain a better result. Yeah, that was just more.
Thanks so much.
Because that was a very important step of the team recommendation.
Thank you.
No problem.
Okay, so it was the first method that we mentioned, and the other method, is based on the message passing. And in this method, generating the embeddings is in different ways. Suppose that we have a graph, skills and experts are connected to each other, and the goal is, generating the embeddings for skill nodes, and then, feeding them to the recommender model. And in the message passing method, the idea is that at first, each of the nodes, initiate with some, vectors, and then in each step, these initial vectors are modified by gathering the information from all the neighbors. For example, S1 has 3 neighbors. After at first it has one, vector as the initial vector, and then the information from all the neighbors are gathered together, and the initial vector of S1 is updated after the first method, first step. In second step, the information of neighbors also is going to be added, and then the embedding vector of the node is updated again. And it can be studied that how many steps is enough for us. And after some steps, the embeddings of all of the nodes are generated, and then these embeddings, same as the previous one, same as the other method, these embedding, these dense vectors, are fed to the model, and the model can recommend the team. So as we mentioned, the method of generating the embeddings, has been different in the recommendation domain based on using the message passing, techniques which are graph neural networks, GNNs, and or using the meta passes to generate the embeddings. If you want to mention more about the GNN methods, we can say that their difference are based on the different aggregation function. As you can see here, gathering the information from the networks, are done by the function aggregation, and then updating the vector of each node is by combination function. So these two functions are important, and different GNN methods have different aggregation and combination function. In general, we can mention the inductive methods. These methods are useful for the cases that we have unseen nodes, and one of the most important methods in this case is GraphSage. And also the other GNN methods, are the attentive models. In these models, the importance of the neighbors of difference, in a way that I told you that in message passing, the information from the neighbors are gathered. But in attentive one, the information came from the important node. have more effect than the other nodes. So the importance of the neighbors are different, can be different, in attentive methods. And one of the important, method in this, category is the model GATT. The other category, of the models in which are GNN based are graphisomorphism methods, and in this, category, the aggregation function and the combination function, both of them are going to be learned instead of using a fixed function at first. That's why GIN, graphisomorphism method, this method is the most powerful GNN method to capture the structure of the graph. All these methods, these different, graph-based, GNN-based methods can be applied, to in team recommendation domain to recommend different, to generate different embeddings and then fit them to the model to recommend the team. And one important research question that that can be talked about is which of the methods is better, and which of the methods works better and leads to recommending the best team, the better and the effective team. And this is the study which is recently done by our team, which is published in WISE. And by comparing different GNN methods for team, specifically for team recommendation problem, we can see that attention-based models, which are GATT, and also HAN, which is the attention-based model for heterogeneous graph. In general, we can say that the attention-based, GNN models works better for team recommendation, and the results on different data sets has shown this, and this is the result on DVLP, and also for both for BNN and FNN, and also the similar result also we have for the other data sets. And the other question that that are answered is that is it the type of the recommender is important or not? By changing the recommender from FNN to BNN, can we get different results or not? And we can say that by comparing the results on FNN and BNN, we can see that in team recommendation domain, there are attentive models, attentive GNN models with FNN leads to recommending the best effective teams. Okay, so these models, these methods that we explained was all of the models that during the time has studied in team recommendation domain. And now I'm going to mention different training strategies that are used in this domain. The first one is the negative sampling. As I mentioned, most of the available data related to the team recommendation only consist of the successful teams. And for example, in DVLP, we have the list of all of the published papers, and so we have data about all of the successful teams, and same for other data sets. That's why by accepting the closed word assumption, we can say that any instances of team which are not seen as a successful can be seen as unsuccessful sample. For example, if we don't find any published paper by the authors E1 and E3 that cover the skills S1, S2, and S3, if we can't find any paper or any result associated with these sets of experts and skills, we can say that we can accept this as a negative sample. And so in the network, we can add the connections by the dash ones, and by feeding the model by negative samples can help the model to learn better, and in compare with only feeding the model by positive samples. That's why this method using the negative samples in team recommendation has been used by different researchers. And as I mentioned, the first term is related to the successful instances in a way that the model learn to generate the embeddings of the skill set and the VE and VS, the vector associated with the experts, the vector associated with the skills close together. And also for the negative samples, the model learned to generate the embedding vectors of them far from each other. And in this way, by providing the model with negative samples, we can help the model to learn better.
I just wanted to add again, just a technical thing, because I personally experienced this, so I just wanted to show what a negative sampling is a very helpful idea. So again, back to this architecture. So again, if you train a model that has a very large output layer, and if you are trying to do, for instance, multi-label classification. So if you have only positive samples, this means that the model tries its best to predict the ones, but it has no loss for not predicting zeros. So for instance here, this is the truth, and if the model tries to, for instance, predict 0 or some probability value, because these are sigma or softmax, yeah? So you're gonna have, for instance, a prediction value of 0.9. So this means that it is close to truth. But if it is 0.1, means that it means false, so there is a huge loss. But this loss only calculated for those that are part of the truth, there are ones. And the last layer is of size the entire candidate. So if you have 2 million experts, this size is 2 million. So, and usually the teams are about 10 members or 5 members. This means that the model is trying to just predict only 5 or 10 ones out of 2 millions. So that's why usually these models have very low performances, because finally the average loss of the entire layer is very low. The loss is going to be very high. So that's why negative sampling tries to say that if we have an additional loss for those that are 0, meaning that if the prediction is 0.9, it means that there should be a huge loss. You should not predict that expert. And so the negative sampling tries to do just simply avoid predicting or recommending an expert which is not part of the truth as an instance thing. So this is again another helpful insight for the model to learn better, or to calculate larger loss in order to predict it better. Yeah, that was just a technical thing.
Okay, the other training strategy that is used by researchers is the streaming strategy. Predicting the future successful team that can work successfully together, is by considering the temporality of something like skills or level of expertise or collaboration ties is hard. The skills and the skill expertise level or the collaboration tie of the experts by time change. So to predict a successful team, it is required to consider these changing in time. It was the intuition to use this strategy, and in this method, the idea is that the model at first try to learn from the instances from one time interval and generate the embeddings, And the generated embeddings of this time interval can be considered as the input of the next time interval. And then in this time interval, the model try to modify the previous, generated embeddings. And this continue to the current time. So the model starts from the past, and in each time interval, the model try to improve the, the quality of the generated embeddings. And we can say that the data streams to the model by considering the time, and so in this way, we help the model to learn from the near past and forget about the, the far past. So, considering the temporality of skills, expertise, and other properties, was the intuition to using this, strategy, which was helpful, and the result shows that by using, this training strategy, team recommendation models can get the better results.